Everyone. So now that we've covered moles and exactly what moles are, let's take a look at how mass, moles, and particles are related to each other. So we're going to be working on some skills here. First off, we're going to work on just one-step conversions using the mole. So we're going to start off with mass and mole conversions. So we've learned before about molar mass. Molar mass again are the grams in 1 mole of a substance, unit given as gram per mole. So you can see in this unit that the gram or the mass is related to the mole, and it's basically related in the molar mass itself. So we're going to be able to use the molar mass to essentially relate moles and mass together. So let's take a look here. We have 10 grams of hydrogen, and we want to know exactly how many moles of hydrogen that is. So when converting, we're going to be using the dimensional analysis method. So the dimensional analysis method, I'll just kind of put some general terms here. You basically have the unit that you're beginning with. Okay, so I'm just going to write have. That's basically what we have to begin with. And we're going to multiply that by a conversion factor. That conversion factor is basically going to be a fraction. That fraction is going to be the unit that we want in the end, divided by the unit that we already have to begin with. You can see that the two halves will cancel each other out, and all we're left is with the unit that we want in the end. This is a simplified way of looking at dimensional analysis, but it's probably something that may help you to kind of visualize and try to do these operations the right way. So if we're starting off with 10 grams of hydrogen, okay, and we want to know how many moles of hydrogen that is. Okay, well, I have grams right now. So I'm going to multiply that by my conversion factor. I want moles in the end. So I have to make sure that I have moles in the end, and I have to begin with grams. So now filling in the numbers, it has to be what I know about hydrogen that relates grams and moles together. Well, luckily we know that molar mass relates grams and moles together. So the molar mass of hydrogen is 1.01 gram per mole. But we have to remember that this is a diatomic molecule. Okay, so basically we have H2. So this 1.01 grams per mole times 2 means that the hydrogen is really going to have a mass of 2.02 grams per mole because there's 2 atoms of hydrogen in H2. Okay, so this 2.02 grams per mole is essentially 2.02 grams for every 1 mole. So this is where I'm filling in the numbers. The molar mass is going to be my fraction here. So 2.02 grams on the bottom because we are starting with grams, and 1 mole on the top that we want to finish with. So we get 10 times 1 divided by 2.02, and that gives us 4.95 moles. Moles of what? Well, moles of hydrogen. So now let's take a look at another example here. I have 30 grams of calcium chloride. This right here, this 3H2O, this is referred to as a hydrate. A hydrate is basically a compound where water molecules essentially attach to whatever compound you have. So we actually call this a trihydrate because there's 3 waters attached. And we want to know how many moles of CaCl2, so calcium chloride trihydrate, we're going to have. Okay, so same approach. We have 30 grams times, okay, in the end, we want moles, we have grams. It's always going to be the want unit over the have unit. That way we can see these gram units cancel each other out, and we're only left with moles, which is our goal in the end. So now again, we need to know what relates grams and moles together, molar mass. So we need to find the molar mass of this very complicated and intimidating looking formula here, but it's really not all that bad. So if we take a look at calcium, this has a mass of 40.08 grams per mole, and chlorine, which has a mass of 35.45 grams per mole. Okay, but we have got 2 chlorines, so that means chlorine is contributing a mass of 70.90 grams per mole. Okay, so the sum of these two is going to be 110.9 0.98 grams per mole. Now this 3H2O component is really just 3 waters attached to this calcium chloride. So I know this dot probably looks familiar. In math it means multiply. In chemistry it means just kind of added on. So the mass of water is 18.02 grams per mole. I have 3 of those. Okay, so we're going to have a mass of 54.06 grams per mole from the water. Adding these together, we are basically getting that the total mass here of this calcium chloride trihydrate is going to be 165.04 grams per mole. Okay, so I have 165.04 grams for every 1 mole of that. So I have in 30 grams of calcium chloride trihydrate, I have 0.182 moles. So it's just a matter of just setting up the units correctly. So let's go the other way now. I have 1.5 moles of CH4 known as methane. Okay, so 1.5 moles of CH4 times, well, now I want grams, so my grams can be on top and my mole will be on the bottom. Okay, so CH4 has a mass of 16.05 grams per mole. I'll let you go through the math to figure that out. So again, it's going to be 16.05 grams for every 1 mole. You can see here that the 1 is now in the denominator rather than the numerator because of the fact that we're looking for a different unit. Our moles cancel out here and all we're left with grams, which is what we're looking for. So we get 1.5 times 16.05 divided by 1, which is 24.08 grams. And we always want to label with the substances as well. So grams of CH4. Okay, so particles to moles is really no different, except this time there's no mass involved. Anytime you do any kind of conversion, you have to kind of know something that relates the two units together. So in this case, we're going to use Avogadro's number. Basically, that 1 mole is equal to 6.02 times 10 to the 23rd particles. Okay, so here we'll actually be able to count how many particles, atoms, molecules, whatever it is that we're going to be having. So let's start off. We have 3.01 times 10 to the 23 atoms of sodium, and we want to know how many moles of sodium that is. Okay, so this will require a little bit of math scientific notation here, but the process does not change either way. So we have 3.01 times 10 to the 23rd atoms. And you always want to make sure that you label the substance as well. This will come in handy later when we get into chemical reactions and stoichiometry, just labeling substances as well. Okay, times, well, we want moles, and we have atoms of sodium. Okay, well, I know that 1 mole is equal to 6.02 times 10 to the 23. Now, particles can be anything. Right? It's not really specific to one thing, just like how 1 dozen is not specific to eggs. It can be a dozen of anything. So particles is basically interchangeable. In this case, we're going to talk about 1 mole is equal to 6.02 times 10 to the 23rd atoms of sodium. So let's just fill that in. 1 mole over 6.02 times 10 to the 23rd atoms of sodium. Do this math, you get 3.01 times 10 to the 23 times 1 divided by 6.02 times 10 to the 23, and you get basically half a mole of sodium. Okay, so the process doesn't change. It is still setting up that fraction, the want unit, whatever you want to finish with at the end, divided by the half unit. But this time we're not using the molar mass. We are using Avogadro's number because what we're looking for and what we have is different. Now we're talking about particles. We're not talking about mass or no grams or anything. So let's take a look. If I have 4 moles of SiO2, silicon dioxide, going to go backwards now. So 4 moles of SiO2. I want to know how many molecules that is. SiO2 is a covalently bonded compound, so we have molecules for the term, not atoms. Okay, so I want molecules, just extend that out, of SiO2. And I have moles of SiO2. Again, we wanted to make sure that we are labeling the substances here. It's just a good habit to get into. So once again, 1 mole is equal to 6.02 times 10 to the 23 of anything. So here it'll be molecules of silicon dioxide. So again, this Avogadro's number is used for anything, okay? It's not really limited to one thing. It's just a way to count the particles here. So if I have 4 moles, well, I know that I'm going to have 6.02 times 10 to the 23 molecules if I have 1 mole. So our math basically comes down to 4 times 6.02 times 10 to the 23 divided by 1, which gives us 2.408 times 10 to the 24 molecules of silicon dioxide. Okay, so again, we're just setting up the units correctly. That's probably the most important part here, just setting up the units, and the rest will kind of work itself out. If you set up the units, you really are lessening the chance of making a mistake on just some kind of like silly error. Okay, so now that we've covered one-step conversions using the mole, let's expand upon that and go to two-step conversions now. So this would be the second skill that we want to master now. So we want to basically be able to convert all the way from mass to particles. Now, there's no direct conversion between them. Okay, there is no just one step going from grams to particles, atoms or whatever. But there is something that they have in common, the mole. They both involve moles, so you can actually use moles as like a bridge between these two. And so the way to do it is basically you're going to convert one unit into moles, and then you're going to convert that unit into whatever else you're going to look for. Okay, so it's really 1 unit to mole, mole to the second unit. Mole is going to be that middle kind of like area there. So let's take a look at the example here. I've got 30 grams of iron. I want to know how many atoms of iron that is. Okay, there is no conversion going from grams to atoms of anything. Okay, so what we're going to have to do is we're going to have to turn our 30 grams of iron into moles and then turn those moles of iron into atoms. Alright, so we're starting off with our 30 grams of iron times, so we want moles. That has to be our first step because there's no way that we're going to be able to find atoms if we don't have moles. Here we have moles in grams. Anytime you see grams involved with moles, it should come to your mind molar mass. Iron has a molar mass of 55.85 grams per mole. So that means if I have 1 mole of iron, there are 55.85 grams. Okay, so 30 grams times 1 divided by 55.85. My 30 grams of iron contains 0.537 moles of iron. Okay, now that we have moles of iron, we can find atoms of iron. Okay, so 0.537 moles of iron times, now we want atoms of iron, and I have moles now. So you can see the moles now in a different location on my fraction because we're transitioning from what we want to what we have. So now we have moles, we want atoms, okay? Well, we need to find out what relates moles and atoms together. Well, again, 1 mole is 6.02 times 10 to the 23 anything. Okay, so in this case, it'll be atoms of iron. Okay, so if I have 1 mole, that's 6.02 times 10 to the 23 atoms. So 0.537 moles times 6.02 times 10 to the 23 means that in 30 grams of iron, I have 0.537 moles, which is the equivalent of having 3.23 times 10 to the 23rd atoms of iron. So it took 2 steps here. We had to convert our grams into moles and then our moles into atoms. Okay, again, moles is that bridge. It is going to be the middle point that we have to get to if we want to convert these two things together. So now let's do one going the other way. We have 4.62 times 10 to the 23 formula units of lithium fluoride, and I want to know how many grams of lithium fluoride that is. Okay, so again, there is no direct link between formula units or particles and mass, so we're going to need to find moles as our midpoint. So 4.62 times 10 to the 23 formula units. I'm just going to write formula here just to kind of condense this a little bit, of LiF times, alright, so we want to have moles of LiF, and I have formula units of LiF. Okay, so once again, Avogadro's number, because it's going to be used for anything counting. So 1 mole contains 6.02 times 10 to the 23 formula units of LiF. Okay, so you get 4.62 times 10 to the 23 times 1 divided by 6.02 times 10 to the 23, and you get that this actually contains 0.767 moles of lithium fluoride. Okay, now that we've got moles of lithium fluoride, we can find grams of that. So we're going to take that, multiply. I want grams. I have moles. Again, grams and moles. We have to think molar mass here. The molar mass of LiF is 25.939 grams per mole. Again, you would just get the mass by taking the mass of the lithium added to the mass of the fluorine. So if I have 25.939 grams per mole, and I have 0.767 moles of it, I essentially have 19.906 grams of lithium fluoride. Okay, so again, we have to go to moles. This is going to be a 2-step thing. Moles are basically like the biggest part, the most important part of chemistry. We're always going to need moles for calculating things because of all the different uses that we're going to have. We are having to compensate for the fact that these elements have different masses to them. So moles are really, really important, and they'll be used just about all the time.